Hi everyone, so now we're going to talk about Math 104, Webwork 9 solutions. This Webwork is going to be based upon the topic of related rates. It's not fairly challenging, but sometimes it's very hard to kind of like wrap your head around problems. So I hope this walkthrough will kind of help you out with this. So now let's start talk about the related rates, like just in general. This is going to be the analysis of dynamics of a situation happening at a point. Okay, so there's going to be a situation given to you where in that situation something's going to be changing with time. Let's say somebody's walking away from you, so the distance between you guys is changing, and then there's a lot of things that you can put them in that perspective. Okay, so what we tend to do in this case is to find the rates of different quantities and try to relate them. Just think about this: if you're putting water inside a tank, you're putting a water at a constant rate. How fast is the height rising? Or maybe you're just like walking away from your friend and the other friend is walking in the other direction. How fast is the distance between you guys changing? And all of those kind of things. Now, to do that, we're going to follow the three-step kind of like approach to this. Every time you see a problem, the first step would always be to find the relationship between the quantities that are actually changing. Okay, so there are going to be some quantities that are constant, some of them that are going to be changing. So you got to figure out which ones are changing, and you have to associate a relationship between them. Most of the time, these relationships could be very easily figured out using basic geometry, something like similar triangles or Pythagoras, or something with familiar shapes like cones, circles, spheres, and all those things. Okay, so there's going to be nothing rocket science happening in finding a relationship. Once you've seen them enough times, you get used to it, and then you know how to approach all these kind of problems, because most of the times the relationships are found by similar approaches. Okay, once you're done with the very first step to find a relationship, the next step would always be to go and derive that relationship with respect to time. So this is going to use implicit differentiation, where you're going to take a derivative of the whole expression that you found out for those quantities that are being changed. You take a derivative of all of those. So now whichever quantity is going to be changing right now with respect to time, its derivative is going to be written as whatever that quantity is, d of that over dt. Okay, so like in this case, if you're changing a volume, the change of volume with respect to time will be written as dv dt. Usually in related rates, we use a shorthand notation of those, which we call v prime. So whenever you see a v prime, s prime, d prime, prime means you have that little extra symbol down there. So if I point it out on this, you'll be able to see. So that little comma on top is actually referring to prime. So v prime represents the change in volume with respect to time. Okay, so we're going to be using these shorthand notations, and once you have all of those, the key step, the very last step in the analysis, will always be to actually identify the moment of dynamic. Because it's a dynamic situation, it will be changing at different rates at different times. So we got to make sure that we know exactly when do we want to evaluate these relationships and the rates between them. And from there we'll go on. I think we'll walk through examples, it'll make more sense. Okay, so question number one is when they're talking about a cube, and then they've given you a relationship between the volume of a cube and its side. Okay, so you have given that thing. And what they said is, suppose in the first part of the problem, the side is just a function of time as just t. So as t progresses, let's say 1 second, 2 seconds, 3 seconds, the side literally becomes whatever that time is. So side is also increasing with time. Okay. So now what they want us to do is find s prime and v prime, which means the rate of change of s with respect to time and the rate of change of v with respect to time. So first of all, in this problem, what they want you to do is to get used to the concept of related rates rather than implicit differentiation. So they've given you an explicit relationship that s is just that. If s is just that, so derivative of s with respect to t is just going to be 1. So s prime is just 1 in this case. However, because volume was s cubed, as we talked about it, then if you plug in that s inside the volume function here, what you're going to get is the volume is just t cubed. Well, if you know the volume is t cubed right now, then you can do here is just take a derivative of that t cubed function with respect to t, and you're going to get 3t squared. Okay, that's for the first part when you assume that s is equals to t. Now in the other part, what they do is they reverse the scenario. They made v equals to t, sorry. So what's happening right now is as time progresses, the volume is increasing. So we got to figure out at what rate is the actual side changing. So first of all, we need to figure out side as a function of time if we're given volume as a function of time. So because of the same relationship, you can now substitute for v into this relationship, and you're going to get this equation down here right now. T equals to s cubed. So once you know that, you can isolate for s by taking a cube root of both sides, and then taking regular derivatives of s with respect to time is going to get you that value. And then derivative of v, that's equals to t, with respect to t is going to give you just 1. Okay, that's like a fairly simple problem, and we're going to start to talk about the other ones where you have to use implicit differentiation. So now, second problem and third problem are going to be focused on watermelons. We're going to talk about both of them together. So what they said is your watermelon has a thickness that's given in a certain relationship with respect to radius. Well, the thickness is always going to be r divided by 10. So thickness of the rind. Rind is this portion, where you have the green portion of the thing which is not edible. I don't know, but yeah, some people try to eat it, but yeah, whatever. So that thing is actually the green region, and the thickness of the green region could be written out by this relationship. The thickness is just 1/10 of the radius. So if you call that thickness, that t that we called up here, what you can do is you can choose either that as a variable, or you can go with my analysis, right? So from that, what I figured out, the radius of the inside part, that's the edible part, could be just figured out as a ratio of the radius that you have for the actual watermelon. Okay, so now given this thing, how do you figure out the volume of this portion here? That's the challenge, because what they want us to do is analyze how fast is the volume changing if the radius is increasing at a certain rate. Now, volume of the rind specifically, they want you to figure out volume, the change in volume of this as the radius gets bigger and bigger. So now if you think about that green region's volume could be written as the volume of the whole watermelon, take away the volume of the inside. Okay, so that's what I did here. When you do the volume of the outside, you get 4/3 pi r cubed, because r is the outermost radius, and then the inside radius is x, so take away 4/3 pi x cubed, and then when you factor out 4/3 from that, that should be the volume of the rind equation in front of you. Now, in our analysis, what we want to focus on is how fast is the volume changing given the change in the radius. Okay, so this expression right now for volume has two unknowns, r and x. What we want to make sure is we substitute the relationship in only the variables of interest. In this case, they're just volume and radius, so we'll need to eliminate for x here, and that's why we got this relationship before. And then when using that relationship, you can plug it in there. Your volume is now purely a relationship between v and r. Once you have that form, this is the first step done. The first step of the analysis is to find the relationship between the changing quantities, and we actually figure that out. Now, second step is always to take a derivative of that relationship with respect to time, so we're going to do that. If you take a derivative of v, here you're going to get v prime, and then all of this is just a constant, stays right here, just like that. Derivative of r cubed is going to be 3 r squared, but there was a 3 at the bottom which canceled out, so that's just a part of the algebra that went away. So you're going to do 3r squared, but because r is also changing with time, you got to multiply by r prime because of implicit differentiation. Okay, so every time it's a shorthand rule. Every time you do a derivative of a certain thing, you have to combine that with a v prime, because that certain thing must be a dynamic with respect to time. Okay, so we got this relationship here. In this, v prime represents the change in the volume, and r prime represents the change in the radius. Okay, so now we have the system. To find a v prime, we need an r and an r prime. Okay, so now r is changing itself. You know, this quantity is changing itself. Well, r prime is constant at the rate given to us as 2 centimeters per week, but the r is changing as you go. So we have to figure out exactly where do we want to evaluate this thing at, right? So we got to figure that out. That's the third step of the analysis. So third step of the analysis, to figure out when do you want to evaluate, the question states it should be after 5 weeks. So you have to figure out whatever quantities that you have in this expression, what are they going to be after 5 weeks? Okay, so we'll try to figure that out. We know the radius is growing at 2 centimeters per week, and then we can just easily say, oh, radius after 5 weeks is just going to be 10 centimeters here. Okay, once you have that expression, you can punch in all these numbers here, and this will give you the rate of change of volume at the moment when the radius is 10, or at the moment when 5 weeks have passed away. Okay, and that's how you finish this problem. The other problem, the question 3, is also the same, but in this case they've given us the opposite information. So all the analysis up to this point is the same. They have the same relationship, same stuff is happening. So now instead of finding the change in volume of the rind, they've already specified this thing to you. In my case, it's 20 centimeter cube per week. Now they want you to find how fast is the radius growing. So in the first expression, they gave us this, they want us to find that. Now they've given us this, and they want us to find that. Okay, so it's going to be interchanged. So let's see how we're going to do that. So all the relationships are the same, the derivative is the same, everything's going to be looking okay. So we have to figure out exactly the moment of analysis, right? So what we have to do is, in our analysis, you remember, all of this expression needs an R. So we need to figure out exactly which radius we're talking about when we want to evaluate this expression. So we have to figure that out first. After 5 weeks, given that this rate is the growth volume, you figure out what's going to be the volume after 5 weeks. And we figured out that's 20 times just 5. So that's 100 centimeter cube. Now, when the volume is 100 centimeter cube, what is going to be the radius could be also found out by this same formula here. So you plug in 100 here and you solve for R, you get this value. This R value is the radius at that moment of evaluation when you're going to use it. Okay, so that's going to be handy when we actually evaluate the expression. So same stuff, once you have the relationship, you take a derivative of the relationship. You have the same thing that you had before, and now you got to isolate for R prime. So when you do that, you move everything towards the left side. What you're going to get is this expression out here. Okay, I multiply a bunch of things to kind of simplify the expression. And now in this analysis, you need your V prime and you need your R. Well, V prime is given to you already in the problem. R is something that we already figured out from this point. Okay, so when you plug this R in there, the final expression for a rate of change of R is going to be given like this. So this problem highlights that you can always move around things. Given that change in one quantity, you can find the relationship and then find the change in another quantity, or vice versa. Okay, all you got to do is make sure that the moment of analysis is correct. Okay, so now let's talk about question 4. Well, you have you and your friend trying to leave a specific path here, where you're starting at this spot and then you go north and your friend goes west. Okay, you're traveling at a speed of V. So this situation represents what's going to happen after t hours. Okay, so if you're traveling at a speed of V per hour, after t hours you're going to be at a distance called Vt. Okay, because speed equals to distance upon time. So distance equals to speed times time. If your speed is V, the distance could be easily figured out by multiplying by the time. Okay, this is after t hours. So given that you're going to be traveling this distance in north and your friend's going to be traveling this distance in the west, what they want you to figure out is how fast is the distance between you guys changing. Okay, so let's see. Once you actually figure out this geometrically, you can see that this is just nothing but a Pythagorean triangle, where you can use the Pythagoras relationship to figure out distance as a function of time. Okay, because this distance is a function of time, that distance is a function of time, so this distance could also be a function of time as well. Once you know that, you can put them in the Pythagorean form. The question recommends you to solve this as much as you can before you proceed, because it'll make your job much more easier. So right now what we got is, when you open the squares up, you factor out t squared and you bring it outside the square root, you're going to be left with just a t. Okay, so in this expression right now, this is the point where we're going to start to take our derivatives, because that's the relationship we were looking for. Once we have the relationship, the derivative of this, because with respect to time, this is all a constant, so this will just go 1 and you'll be left with this as your derivative here. Okay, and now that derivative is a constant, it makes sense, because if you are traveling at a constant speed towards north and your friend's traveling at a constant speed towards the left or the west, well, the distance between you guys are also going to be changing at a constant speed, because you're not speeding up throughout the journey, right? So that kind of makes sense. So this is the actual speed that's going to describe the difference between your distances, right? And now from that point onwards, you got to take the second derivative as the problem states. So if you take a second derivative of a constant, it's always going to be 0. So that was a very easy calc. So that's why they want you to kind of simplify this, so you can see this very clearly. Okay, now this is the part where people mostly have trouble with, so I want to try to explain this. Well, the second situation says you're going to be lingering for an hour to figure out a special spot. I don't know for what reason, but yeah, whatever. You'll be figuring out a spot and your friend has already left. You start an hour later and then you got to find out what's the distance between you guys going to be. Okay, so now when the person left after t hours, the distance for that person is just going to be wt, because that person is still traveling like it was supposed to be in the previous case. But however, for you, because you start an hour late, you gotta have to stop. You gotta take away the distance that you would have traveled in that hour to get there, right? So think about this. If you also started at the same time, you were gonna travel VT. But now because you're traveling like an hour later, essentially you lost the distance that you were supposed to cover in that hour, okay? So what was the distance that you were supposed to cover in 1 hour at the speed of V was just gonna be V. So this expression right here will just be your regular distance, but take away V from it. So Vt minus V, which you could simplify to be that way. Okay, so that's how this is going to be. Most of people kind of think where you add a W here, but that's not going to make sense because that W distance is because of the speed that the other guy is traveling at. But who started late was you, so that effect should not be there in this case because they should have been just traveling at the speed that they were supposed to. You traveled a little bit later, so you keep the loss to yourself. That's why you have V of t minus 1. So again, we're going to do the same analysis. Now instead of having a very nice function that we had in this case, we're going to have a nastier function because we have a different situation here going on. So if you compose the same distance using Pythagoras again, you're going to get this expression. If you take a derivative of this using chain rule and a bunch of stuff, what you're going to get is this expression here, which could be later on simplified to be this thing. So it's all algebra, nothing crazy, all the basic stuff that you do. All you gotta do is treat W and V as constants. Everything else, which means just T, is a variable. Okay, so that's doable, not gonna be that bad. But then again, you gotta do the second derivative as well. So it's just a mere challenge of algebra, nothing conceptually crazy. So once you take this one out, you gotta take a derivative of this. In this case, you're gonna use quotient rule and chain rule both. So when you do that, you're going to get to this expression, which when simplified comes out to be this thing here. Okay, I encourage you to practice it, but at the end you can also submit this answer because they're the same for everybody. But I would recommend you to give it a shot so you get better at analyzing things in this way. Alrighty, so let's go to question 5 now. That question is about a policeman and a driver. Okay, what's happening is the policeman is traveling north upward from the spot on there, and the driver is to the right for the first part of the situation, and they want you to figure out if you are speeding up there at a speed and this person is speeding to the right, what you have to find out is how fast is this guy moving towards the right, given that how fast is this distance changing. So in this case, step number 1, we have 3 quantities that are changing. We have to figure out a relationship between them. Again, nothing rocket science. With geometry you can easily figure it out. We call that distance x, I call that y, that distance is d. So once you do the Pythagoras, very easy to figure out that the relationship between d is just square root of x squared plus y squared. Okay, and now once we have the relationship, the second step is to take an implicit derivative. I did that, so once you take a derivative with respect to time, you're going to get that expression evaluated here. So remember, again, we talked about it before, when you're taking a derivative of x squared, it's going to be 2x times x prime, because x is the quantity that changes with time. So always watch out. Once you simplify expression, it looks like this. Okay, so now in this case, what you gotta see is a subtle thing inside related rate problems is that whichever quantity that you chose, in this case specifically y, if that speed is given traveling towards north, try to see what that implies towards the quantity that you have. Well, as time progresses, y is going to get smaller and smaller, right? Because if that's the distance of the policeman from the origin, it's going to get smaller and smaller. So effectively, whatever speed the policeman is traveling with towards north is going to be decreasing y. So we're going to treat that as a negative quantity for the rate. Okay? And then the distance between the person and the policeman is increasing at the given rate. So we're going to choose a positive quantity. In my specifics, what they said is the policeman is traveling at 50 miles. So because it's traveling north and the context is telling me that the y is going to decrease, I'm going to use a negative 50 here. We're trying to figure out x prime, which is a representation of how fast is x changing, or in other words, how fast is the passenger moving away. Okay, we're given the d prime, which means the rate of change of this distance is 30. It's positive because it's increasing, and that's cool as well. And we need to figure out which point do we need to evaluate this, because there are different distances at different points and different rates. The point of analysis that they want us to do is when x and y both are half a mile away. Okay, so we have all the information we need. We needed x, x prime, y prime, and this whole situation. We have all of them here labeled out. So all you gotta do is plug it in and solve for x prime. When you plug it in, do just regular algebra. You get your x prime needs to be 50 plus 30 times square root of 2. Okay, that's the rate at which the person is traveling, and it makes sense. Is the rate positive? Yes, it is positive, which means you are going to be actually increasing towards that side, and the x is going to increase, which makes sense in this context. So now, if the radar gun in the second context is when the radar gun reads negative 30, what that tells you, the person is approaching this side, because if you're going up here, the person is approaching, then distance is going to become smaller and smaller amongst you guys, right? So given that fact, the only thing that's going to change in all of this context is right here. Whatever you plugged in for D as 30, you plug in negative 30. So consequently, if you do the same analysis again, all you're going to get is just 50 minus 3 times the square root of 2, which I guess is a negative number or somewhere close to it, a very small positive value. But yeah, it makes sense because you're going to be starting to approach this point. Okay, and that's question 5. Question 6 is also kind of standard as well. This is what you'll see in most of the calculus problems. In this case, you have a spotlight on the ground that is 12 meters away from the building, and there's a person who's 2 meters tall walking towards the building at this given speed. What's happening here is the light from that person hits the building, and then there's a shadow that's being formed. As you approach the building, what's going to happen to the shadow? The shadow is going to start to decrease in size, right? What they want you to figure out is how fast is the shadow decreasing if she's walking at this speed when she's 2 meters away from the building. So we got all the pieces of information we need. First of all, we need to know which quantities are changing. The spotlight's fixed, the building's fixed. The only thing that's changing is the position of the person with relative to the building. So we're going to call that quantity x here. And the length of the shadow is changing. I'm going to call that s for this context. Okay, so we're given all this information. We can easily figure out the basic stuff here. The distance from the spotlight to the person is going to be 12 minus x if the whole distance is 12. So that was easy as well once you figured it out. In this case, you can't use Pythagoras. So the other tool that I want to introduce here is similar triangles. The tool of similar triangles is very easy. It's just saying that this triangle here that's being formed is just a scaled down version of the bigger triangle. Okay, so they should share the same proportions. So what you can do is, if you take the ratio of this side, so height of this guy over base of this guy, that must be the same proportion for the height of the big guy over the base of the big guy. Okay, so height here is 2, so you're going to go there as a 2 there. This base is 12 minus x, so you're going to get 12 minus x there. This height is s, so that's going to be s, and the whole distance is 12, so that's going to be 12. So this here, right, we got a relationship from similar triangles. Once we have the relationship, the next step is to derive this implicitly with respect to time. So I isolated for s, I took the derivative. Feel free to do whatever you got to do. Don't forget to have an x prime added up there because it's a dynamic. So now again, as this thing is moving, as this person is moving towards the building, the consequence of that is that the x is decreasing. Okay, so if I'm going to take the rate dx dt, I'm going to take it as a negative rate. So x prime is going to be negative 0.06. At what moment do we want to analyze? When x is 2 meters, when she's 2 meters away from the building. So all you got to do is punch in all these numbers into this expression, and when you evaluate it, you're going to get a negative 0.144 meters per second. Now, what they want in the answer is you got to take the negative from the answer and just absorb it in the context. What they said is, how fast is the length of the shadow decreasing? The rate of how fast it's decreasing is just that number. The fact that it's decreasing is given by the negative sign. So they already imposed the condition that it's going to be decreasing. So all you got to do is just take that number and submit it without the negative sign. Okay? Because they took the context out of this. And that's straightforward as well. Now let's talk about question 7. Super easy problem. Nothing crazy here. You have a relationship between x and y, where xy is just minus 1. They've given you what the y prime is. They've given you what the x is. And they want you to find x prime. So now let's try to take this. We already given the relationship. The first step is already done for us. So when you take a derivative of this with respect to time implicitly, because x and y are both variables, you got to watch out with the product rule. Okay, this is where most of the people kind of just like think about it this way, or they're going to like label this to be x y prime plus y, where you're not taking a derivative with respect to x, you're taking a derivative with respect to time. So in this case, x will become x prime, y will become y prime. So you got to use product rule here. You get x y prime and y x prime. That's the actual derivative. Now to figure out the x prime, we need to isolate for it. So I figured it out. It should be negative x y prime over y. So now at this moment, what do you need? You need the x value that's given. You need the y prime value that's given. The y, however, is not given. So you gotta solve for it. Well, you know when x is equals to 1, it should obey this relationship as well. So all you can do is you can isolate for y from here, which should just negative 1 over x. So when you plug in x equals to 1 here, you get y equals to 1 as well. That's how you get all the things that you need here. And once you plug it in, all you're gonna get is just this value, negative 3. Very straightforward, nothing hard to find. Okay. Question 8 is now talking about a conical pile where you have something being dumped into at a rate of v prime here. And it's a very special kind of shape because it has a condition on it. The condition is that the height of the pile is always equals to the diameter of the pile. Okay, that's a cool thing to know. We'll see how it's useful later on in this thing. They want you to figure out how fast is the height changing when the height is itself 30. I think 30 or 20, yeah, in this case in 20. So they want to figure that out for you. And let's see how we're going to do it. So volume for a cone has this relationship, right? It's going to be, I think I kind of miswrote it, but I'll correct it here. The relationship should just be 1 over 3 pi r squared h. Okay, now in this case, you have a radius and an h and a v. There are 3 things changing. Now, that's the good relationship, but we want to make sure that our relationship only consists of the variables of interest. In this case, the variable of interest is just the volume and the height, because we're just trying to evaluate how fast is the height changing when the volume is changing at that rate, right? So we somehow have to get rid of this r from the situation. And good thing we already know that the question gave us the height is just equals to diameter. From there you can solve that h equals to 2r, and r in terms of h could be figured out very easily. Once that r goes into this expression will become this, which happens to be resolved to be that one. Okay, forget about this. I don't think we need this one, but I'll cover that up later. So the actual volume is just going to be that. Let me just get rid of this so it doesn't cause any confusion here. So we got this as a volume expression here. Nice, with terms of h. So now we have a relationship only in the variables of interest. We can take a derivative at this point with respect to time. So remember, v prime is just going to be the derivative of volume with respect to time. In the other case, you're going to have 3h squared times h prime. The 3 and the 12 cancels out to give you 4 at the bottom. So just mere algebra, nothing crazy. You can do it yourself as well. And then you plug in the value that you know at the moment of analysis. In this case, when you h prime, you isolate for it. You're going to get is 4v prime over pi h squared. Given that information, what you need is you need to plug in the v prime and the h at the moment to get to the point that you want to solve. When in this case, my v prime was just 50. It's given in that rate, and then the height was 20. So I plug in those numbers and I solve for it. A very easy piece of cake. Okay. Now this is the last one. This is supposed to be the hardest problem on the Webwork, but it's nothing crazy if you are able to conceptually visualize what's happening here. So you have an isosceles trapezoid trout shaped like that. So it has a volume that's given out to be. We can calculate that, and they want you to figure out when the water is being poured into at a certain rate, how fast is the height changing. Again, the same situation. So you want to eventually get to a relationship which only relates volumes and heights. Okay, so I kind of made a picture of this. When you're just having water being poured into there, the water is going to take a shape like this that you see over there. Okay, now for any quantity, the volume is always defined by the area of the surface, okay, times the length that it goes down there. Okay, so we're trying to figure out an expression by ourselves for the volume, and let's see how the dimensions work out. For me, the dimensions for this case is just 80 centimeters. The bottom is 30 centimeters, which I have to convert in meters because the answer is asking for eventually in meters per minute. So it's better to convert everything in meters and then make sure your volume is also given in meter cube per minute. So then it's very easy for us to solve in the given units that we need. Okay, so now let's try to begin this. We got this dimension here, 0.3 here, and by a little bit of math, you can say the remaining part is just going to be 0.25 and 0.25 here. Now in this case, the water is just this face, right? And the water is going to have a height h. Well, these quantities on the side, like these little quantities, I'm going to call x because the symmetrical is going to be the same. So my agenda is to find this area, okay, first, and then multiply by the length that's given out to me to be as 10 meters, so I can easily figure out the volume. Okay, so the surface area could be composed of these three things. You have a A, you have a B, and a C. Well, A is just a rectangle in which the length is 3 and the width is h. So the area here for the water's face is just going to be that for that term. And then for the triangle B and C, you're going to get half times base times height. In this case, the base is x and the height is h. So you're going to get half xh. Now, because you have two of them, you got to add them up. So half hx twice of that is just going to be hx. Okay. So right now, my volume could be easily figured out. So I know the area. I can just multiply by 10 to actually figure out the volume. But hold on for a second. We need to make sure our variables are in order for the interest. Okay. In this case, we have an x. We don't need it because we're only solving for how fast is the height changing when the volume is changing at a given rate. So my ideal expression would be to have everything in terms of h for volume. So let's see that. Now, if you observe here in this triangle and these situation here, you can do similar triangles. In this case, the proportion of the height and the base here and the height and the base here, right, is going to match up. So in this case, this is 0.5, 0.25. So this proportion is just going to be 1/2. So 0.25 over this is equals to that over that. So this is the relationship that you will get from similar triangles again. From this, you can easily figure out this x is just h/2. Once you have this relationship, we're going to punch it in there. And now my volume expression is just going to be that. Because h times h/2 becomes h²/2. Okay. Given that information, the length is 10 meters. So now the volume is just surface area times the length. So I figured out that that's going to be my situation here. Once you have it, now this is the very nice relationship. Once you have simplified it enough. Once we got to the relationship, the second step is just textbook procedure. You got to take a derivative of this expression with respect to time. So derivative of 3h is going to be 3h prime. The derivative of 5h² is going to be 10h h prime. Okay, don't forget the h primes because it's very important. At this situation right now, you have your relationship given out to you. From this, you can isolate for h prime by moving stuff here and there. You can divide both sides by 3 plus 10h here to isolate for h prime. Once you have a h prime isolated, you're looking for that at a very specific moment. And let's figure that out. In the question, they told us to figure out when the v prime is this. So we got this value over here. And at a specific point when the height was 30 centimeters. So in meters, that should be just 0.3. So you're going to plug that h there. And once you have all of that thing formed out, you should be able to get to the expression very easily. So that's it. That's for the homework of related rates. There's not a lot of questions here, but you can always refer to work that I do here. And yeah, if you have any other questions, you know how to reach out to me. Thank you so much for watching.